After a 4-year hiatus, I'm back for another summer of math exposition. Last time I was here, I shared some cool things about the Fibonacci numbers. Today we're going to be using a lot of Desmos, which makes it really easy to compute recursive sequences like the Fibonacci numbers. Today's material started from trying to teach imaginary numbers to students in a pre-calculus class. Desmos also supports complex numbers, visualizing them geometrically in the complex plane. People first viewed imaginary numbers as a weird trick to solve complicated algebra problems, but they're deeply entwined with fundamental physics questions, like understanding the oscillations of this spring. Unfortunately, most discussions of these oscillators would need to use ideas from calculus. These differential equations are some of my favorite examples of why nature really needs complex numbers. But you can't teach kids about differential equations if they haven't learned derivatives yet. It turns out recursive sequences like the Fibonacci numbers can create similar dynamics. Fibonacci uses the coefficients 1, 1, and today we'll be exploring how different coefficients can change the dynamics. We'll even see today that we can use these Fibonacci-like equations to compute pi. To get there, we will take a trip through the beautiful geometry of complex numbers, where doing arithmetic with imaginary numbers naturally leads to shapes like spirals. Today's lesson is split up into 7 scenes, where I'll be showing material from Desmos notebooks which you yourself can open and play with. In fact, 6 times during the lesson today, I will explicitly ask you to pause and play with some of these yourselves, which you can do down in the links in the description of this video. Ready to get started? In our first scene, we will see how simple population equations can lead to expected and then pretty unexpected behavior. Here's a quick problem to get us started. We start with a population of 100 bacteria, where 20% of them will reproduce every generation. At generation 2, we'll have 20 new bacteria. Then 20% of that will give us 24 new bacteria, bringing us up to 144 at generation 3. 20% of that is 28.8, which is, well, not a discrete number, but if we're interpreting these quantities maybe as like grams or something, which we can visualize here as area, it makes perfect sense to add 28.8, bringing us to 172.8. Then after one more step, we'll be at 207.36. Can you figure out an expression that exactly predicts what these values are? So we start at P1 equals 100, and then the population at generation n is the population at generation n minus 1 plus an extra 20%. Given this recurrence, Desmos will make a table for us. Adding 1 plus 20% is the same as adding 1.2, so this is an easier way to write the same equation. And if we start from 100 and multiply by 1.2 4 times, that's just taking the 4th power. The exact formula comes from starting at 100 and then multiplying by 1.2 n minus 1 times to reach the population at generation n. Now let's put the birth rate on a slider to see the effect of increasing the birth rate up to 40%, or of decreasing the birth rate down to 0. We can change gn to match. And also put this point on a slider so we can see as many points of the solution as we want. Adding some automatic zoom lets us watch the runaway effects of exponential growth. Our population reaches 1 billion by generation 239. Our y-axis is on the scale of hundreds of millions and billions, but that makes it really hard to see that anything actually happened before generation 150. Let's open our controls again, and rather than making y change with the population size, we're going to use the more options and put the y-axis on a logarithmic scale. Here we see the hallmark pattern of exponential growth. It's a straight line on a log linear scale. That's because taking a constant number of steps, say 50, will increase you by a constant amount in the multiplicative logarithmic axis. Increasing the exponential growth rate makes the line steeper, and decreasing the growth rate makes the line shallower. How can we make our model more realistic than just runaway exponential growth? Well, let's add a death rate. Let's now subtract the death rate from the population at the generation before. Sure enough, increasing the death rate slows down the growth, up until it stops growing at all, and then starts actually decaying. This isn't actually changing the type of equation we have though. We can just factor up on top. So subtracting the death rate still gives us a general solution that works. If the death rate is bigger than the birth rate, then this exponent here is going to be less than 1, so its powers are going to decay exponentially. Whereas if the death rate is less than the birth rate, then we have something bigger than 1, and we still have exponential growth. Now I'm going to make a modification to our equation, which will make it a little more interesting. Like the Fibonacci sequence, we're going to have a recurrence that relies not just on the term 1 step back, but 2 steps back, So I'm going to make this n-1 instead an n-2. What effect do you think that'll have? And if you want to sort of tell a story about what this equation is now going to say, we could say rather than subtracting the death rate from the population 1 step back, it's going to be from the population 2 steps back, because only then is the population old enough to die. Well, let's see what happens if we do n-2. Well, technically nothing happens. What's wrong here? Well, Desmos is trying to ask for generation 2 by looking back to generation 0, but there is no generation 0. So if we want to say that no one is going to die yet in generation 2, we should say that p of 0 equals 0. And that fixes our problem. So what change did this have on our model? Well, if we look closely, we can see that we're actually growing slightly faster now. Intuitively, that makes sense. Because the deaths are a little bit delayed, the births can get a little more ahead of the game. Moving the birth rate up to 20%, we can see the effect is more pronounced. When the death rate is less than the birth rate, we actually have a stronger gain and we're growing faster than the predicted model. And as we move the death rate past, well, it looks like when they're both 20%, it's still leveling out. And then past then, we're actually decaying even faster than the naive formula would suggest. It doesn't match our predicted formula, but the population still looks to be a line on this scale, so it sure seems like it's exponential growth and decay for all of these parameter values. The question is, what is the growth or decay rate? Now let's try to change our guess function to just fit the growth to some unknown base b to the n. Moving this line around, it seems like 1.11 is the closest fit I can see here. Zooming back in, we can see that this curve makes a pretty good fit, but it's not perfect, especially at the start. Things get even worse when we remember that technically p of 0 is 0, whereas our guess g function is nowhere near hitting that point. Can you do a better job? Can you find some function that's going to fit this curve better? Can you figure out the relationship of what's happening as we move the birth and the death rate? Now it's your first chance to pause and play. Click the link in the description below for scene 1. You'll be able to move the points around and change the sliders like I've been doing. There's some questions down here for you to ponder. And don't forget that you can take a look at putting y onto a logarithmic scale. We can also see more closely that when the birth and the death rate match, the population really is starting and then leveling out. We can lock the death rate equaling the birth rate to check our conjecture. And sure enough, for all values, we see the population leveling out. Let's crank the matching birth and death rates even higher. Now up to 90%, we see the population limiting to 1,000. But we can see how unstable this limiting behavior is. Nudge the death rate down just slightly, and our population's growing again. Nudge it up slightly, and things are dying out. Even pushing to just 90.1% death rate is enough to send the population plummeting back down. Here's what that looks like on our log scale. Lower death rate, exponential growth. Higher death rate, exponential decay. But again, we still have a nice line, so everything seems to be making sense. Pushing our death rate higher and higher, we get a faster and faster exponential decline. Up until... wait, what's happening here? This doesn't look like a line anymore. Here we are at a 90.3% death rate, and the population seems to just be disappearing entirely. But wait, it gets even weirder. It is reappearing. But where'd it go? Between steps 133 and 268, it seems to have just vanished. Zooming out more, the population in this gap is really nowhere to be seen. And as we push the death rate even higher, that disappearing point gets earlier and earlier. And wait, now there's a second disappearing gap? This is getting pretty weird. Let's take a closer look at a 90.5% death rate, where the population seems to disappear right after step 59. So what is happening at step 60? Now let's watch the fate of our population back on a linear scale. We start by growing, but then careen down towards extinction. And what happens at step 60? Well, our population blows right over the x-axis and becomes negative. That explains why it vanished here on the log scale. 0 would be at negative infinity, and there is no place for negative numbers on a log scale. So what does this mean for our population story? Well, it doesn't actually make any sense. You can't have negative population. So these equations are no longer modeling any real population story. But that also makes sense. You You can't have the death rate keep exceeding the birth rate for arbitrarily long. So somehow this rate of decline is so fast that the equation sort of can't steer it back and keep it positive. But this is a lesson about math, not biology. So let's just throw off our biology hats, but keep our mathematician hats back on, and keep exploring these equations, because they're about to do something pretty weird. The sequence actually turns around and heads back towards 0 from below. And zooming over to the right, we can see it actually becomes slightly positive again, although it's pretty hard to see. Going back here to the log scale, we can explain these humps a little bit more. We have alternating regions of being positive and negative, positive and negative, positive and negative. And when we're positive, we're getting closer and closer to 0. We can watch things play out, drawing these humps one at a time. So what kind of function is this? Well, the picture gets even more clear if we crank the death rate all the way up to 95%. It's an exponentially decaying sine wave. What if we just keep taking the death rate higher? Well, things are getting really weird now, and now the death rate is even bigger than 100%, so that really doesn't make biological sense, but what the heck is this equation doing? Things get even weirder if we crank the birth rate up higher, up to 99%. It's hard to see what's going on here, but if we stretch the y-axis, we can see we actually now have an exponentially growing sine wave. The 99% birth rate zone is very weird indeed. If the death rate is smaller at 98%, we still grow exponentially. Then kicking the death rate up, we still see the same behavior. Once it matches at 99%, the population is all of a sudden now barely leveling off. And then just a nudge will kick it down into this exponentially decaying sine wave. Then at some point it goes from exponentially decaying to exponentially growing. So we have 4 different regimes, all in this narrow band of parameters. Exponentially growing sine wave, exponentially decaying sine wave, leveling off, and exponential growth. How can we explain that? In our second scene, we will look closer at these mysterious recurrences with periodic behavior. Now here's a fresh notebook where we can see the behavior more clearly. Throwing away the birth and death story, we're just going to call these constants C1 and C2. So the last regime we were looking at was C1 was 1.99, C2 was negative 0.99. So this is when the birth and the death rate matched. We've also now just made the initial conditions 0 and 1 to make it look more simple. And as we saw, when these match, it's leveling out at 100. But then dragging it down even slightly, we move to the decaying sine wave. And as C2 gets more negative, it goes from decaying to growing exponentially, with a cutoff value at C2 is negative 1. At exactly negative 1, it doesn't grow or decay. We can see the amplitude stays constant. But just nudging it a little bit off will make it either decay or grow. The decaying case has a nice connection to physics. A weight bouncing on a spring will produce a sine wave, and the decay we're seeing corresponds to the effect of friction. Changing the decay rate was reducing the effect of friction. This perfect sine wave at C2 equals negative 1 corresponds to no friction. And then if we go past then, well, this exponential growth would be like anti-friction. Again, that doesn't really make any physics sense. So let's just throw off our physics hat and just keep our mathematician hat on and explore these equations a bit more. Let's choose some nicer round numbers, bringing C1 up to 2. And now let's move C2 back to negative 1, where we saw it was a perfect sine wave. Now what's the amplitude of the sine wave? Well, zooming out, we see that it just keeps growing. In fact, it's growing along a perfect line. Looking closer at the data, we can see that now P of n is just the identity function. Now this is something we can prove. Do you see why we get the identity function? If we pull a Pn minus 1 to the other side, then this equation says the difference between two terms must stay the same. This forces the sequence to be a line, and changing the initial conditions will change the slope and the intercept of that line. If we nudge C2 slightly, it'll bend the curve up. And now it's growing exponentially, which looks like a line on a log scale. Now let's try to bend the curve down slightly. This again is going to make it negative. Negative 1.01 still gives an exponentially growing sine wave. So what if we scoot it up even closer to negative 1? Well, this sine wave is still growing exponentially, just with a much slower rate. And as we push even closer to -1, it looks like we're just rescaling the sine wave. Let's take a closer look at this exact curve. Again, it's defined by p of 0 is 0, p of 1 is 1, and then p of n is 2p of n minus 1 minus 1.000001. It sure looks like a sine wave. And what's the amplitude of this sine wave? Well, looking at the graph, it looks really close to 1,000. But if we check more carefully, we can see that it hits a first peak of 1,000.78 at step 1571. And then it goes down to -1,002 at step 4,713. So the amplitude is still growing. And then when we go back up to 1,003. The other key property of a sine wave is the period. It looks like a full cycle takes a little over 6,000 steps. Focus on where the curve first becomes negative. Step 3,000, it's still positive. Step 3,100, it's still positive. But step 3,200, now we've gone too far and it's negative. Zooming in much further, we see the last step where it's positive is 3,141, and the first step where it's negative is 3,142. We can also ask Desmos to draw a line between those 2 points to find the best guess for where it really crosses the x-axis. Scooting a point along the line, it looks like our best guess for the intersection is about 3141.59. It's reading off the digits of pi, 3.1415926. Well, we actually see it's not perfect. If we drag up to 0.5926, that's actually not as good of an intersection point as 0.5937. So something about this approximation isn't perfect, but it did give us the first 5 digits after the decimal point of pi. Now it's your second chance to pause and play, with the link for scene 2 down in the video description. We have 3 special cases where C2 has 1, 3, and 5 zeros before the 1. Can you see how each of those cases are related to pi? The first case is crossing the x-axis between steps 31 and 32. That's pretty close to 10 times pi. Adding 2 zeros, we have the middle case where the intersection is just after step 300. The closest point is 314, really close to 100 pi. And then we saw our final case crossed at step 3,141, which is really close to 1,000 pi. So each case is scaling out by a factor of 10. And we're adding zeros, which has to do with base 10, so that makes some intuitive sense. But we have to add 2 zeros just to magnify by a factor of 10. So where's that relationship come from? We really want to understand the 3 mysterious sine wave sequences we just saw, but unfortunately that's just a little too tricky of a question to dive straight into. So first, we're going to look at 3 specific examples from our birth-death population equations, where we will be able to guess our way to an exact solution, and through that learn the key secret of how to solve these recurrences. They're all going to have a 20% birth rate. Bringing the death rate up to 11%, we see it's still growing exponentially. We'll call that sequence P1. Bringing the death rate to match the birth rate at 20%, we'll call that sequence P2. And finally, with the death rate up to 27%, we have P3. Like before, we can change the initial conditions by dragging these points. It looks like no matter where we set them, P1 grows exponentially, P2 levels off, and P3 exponentially decays. Now we have another chance to pause and play. Click the link for scene 3 down in the video description. Get started exploring these sequences for yourself and see what patterns you could observe. We again have the option to fit a blue guess curve G of n, and as this scene plays on, I'll give you hints for how to exactly fit each of these curves. Well, the patterns will become a lot more clear when we look at y on a log scale. The green P1 is growing exponentially, the red P3 is decaying exponentially, and the purple P2 is staying the same. And it seems like no matter how we change initial conditions, that growth rate doesn't change. Here's a guess function G of n to help explore those sequences. Little b is the base of the exponential, so positive is sloping up, negative is sloping down, and capital B is the constant offset that controls how high or low we make the line. Let's start with P1. What is its growth rate? Well, the slope seems to be constant, and if we move this base up to 1.1, we can see that that is indeed parallel. So it seems like this is growing like 1.1 to the n. And going back to our original initial conditions on a normal scale, we can see that the exact function 1.1 to the n almost perfectly fits. Let's compare p1 with our guess 1.1 to the n. Do you notice what the error is? The errors are exactly decreasing powers of 1/10. So subtracting off 0.1 to the n, we have an exact answer. But could we solve this for other initial conditions? A nice choice to look at next is going to be to drag the first 2 points to 10 and 11. Moving back to a log scale, this puts the points perfectly on a line. It's just 10 times 1.1 to the n. And again, changing the initial conditions doesn't change the slope. Up until, wait, whoa, what happened here? If we start from 10, 1, our population is perfectly dying out in powers of 10. Shifting our guess down to 0.1, we can see that this perfectly fits the curve. We can see the lines perfectly matching on a log scale. Okay, one more challenge. What if instead we start 10, then 2? Well, now it's back to growing again. Can you see what an exact formula for this case would be based on the last two that we did? The key idea is to remember that 1.1 to the n minus 0.1 to the n was the solution for the starting at 0, 1 case. If we add the solution 10 times 0.1 n that we had before, and we can see it perfectly matches. So how do we make sense of this solution here? Well, this first part is solving the initial conditions 0, 1. The second part is solving the initial conditions 10, 1. And because we can solve each of these, if we add the two solutions together, that solves the one where we add the initial conditions together. 10, 1 plus 0, 1 is 10, 2. Note that our solution is now a combination of 1.1 to the n and 0.1 to the n, where it's 1 copy plus 9 copies of 0.1 to the n. So it's a linear combination of these two exponential growth rates. This is true in general. This is why these are called linear recurrences. So the general theory is that there are 2 degrees of freedom to choose your initial parameters here, your constants a and b, and there's also 2 degrees of freedom in your initial conditions. And for every set of initial conditions, there'll be some matching set of constants, and vice versa. As one more example to show what I mean, what if instead we started from 1, 1? Well, if you solve a system of equations, you can determine that 0.9 for a and 0.1 for b will perfectly match. So these don't necessarily always have to be integers, but again, there's going to be some pair that'll match whatever initial conditions you give. Okay, now let's take a closer look at P2. For the initial values that we first looked at, it seems to be converging to a value of about 1.25. And if we change the initial conditions, we can see some other things. Well, starting from 1, 1 is not very interesting, it just stays all 1. But this is actually reflecting a key point. One of the solutions, one of the exponential solutions, is actually just going to be 1 to the n. And here we see the 1 to the n function actually works. Moreover, now if we change the initial conditions, it's going to change what it limits to, but changing this offset could match the eventual asymptote. But how can we figure out what that asymptote line should be? For example, for our initial values, how could we have known that 1.25 was the exact value we need for this a? Well, we're not going to know that until we also find b. And for that, we're going to go look back on a log scale. Playing around with the initial points on a log scale, we see it keeps converging to some initial value. Except actually, if we move one of the points high enough, we notice that it, well, actually disappears entirely. What just happened? Well, if you actually notice, this corresponds to some of the answers becoming negative. So it is possible for this initial condition, the population actually gets sent negative. Which again doesn't make physical sense, but the equation is totally valid. Moving around a little more carefully, see what happens if we start at 10, 2. On the barrier right before we would go negative, we're instead decaying exponentially. The constant capital A is controlling what this converges to, but if we set a to 0, then it's going to be converging to 0. And then b here is going to control the rate of convergence to 0. And what we see here is it's actually decaying at a rate of 0.2. And if we get the right starting value of 10, we have again perfectly matched this condition. And here we see that perfect curve on a linear scale. Now let's go back to our original question. How could we have figured out that 1.25 was the perfect value that a would need to be to fit this curve? Well, again, by linearity, if we scale the whole thing up, if we multiply the initial conditions by 4, well, then we just multiply everything by 4. So let's instead look at this question: how do we know that 0, 4 should actually limit here to 5? Well, a is going to need to be that limiting value of 5, and then how far off are we from the limiting value? Well, we're 5 below, then we're 1 below, then we're 1/5 below. The initial amount off is actually -5. And setting b to -5, we again see we perfectly match the curve. Okay, one final case, the exponentially decaying P3, where now we need to find both constants little a and little b, which again we're going to look at on a log scale. We see one regular decay rate, and fitting the curve to 90%, we see that fits the slope perfectly. And starting the initial conditions at 10.9, we see a perfect 90% decay rate. Moving the sliders more, we notice a possible decay rate of 0.3. So that's our decay rate little b. And dragging the constant big B to 10, we see it perfectly fits. So in summary, all of these equations have a general solution, which is a linear combination of two exponential growth rates, a to the n and b to the n. For these three examples, because b is less than 1, the b to the n term will just go to 0. The difference in behavior is explained by the a terms. For the first one, a to the n grows exponentially. For the last one, a to the n decays exponentially, so both terms go to 0. And finally, our middle case, when the birth equaled the death rate, a was 1, so it neither grew nor decayed, and we reach a stable limiting value. For these examples, we just found those constants a and b by guess and check and numerical exploration. But was there a systematic way that we could have calculated those two growth rates, a to the n and b to the n? Now that we're warmed up, let's see the general theory for how to find those values and solve these recurrences. So how can we systematically find those growth rates, a and b? The idea is to assume there exists some growth rate, x. In that case, p2 of n, if it's solved by x to the n, is going to have the form x to the n. p2 of n minus 1 is going to be x to the n minus 1. And then p2 of n minus 2 would be x to the n minus 2. Can you see how to solve this for x? Well, if this is true for all values of n, it's true for n equals 2, which just gives us a quadratic. X squared equals 1.2x minus 0.2. Well, that's just a quadratic. We need x squared minus 1.2x plus 0.2 to equal 0. Factoring, we can see that the two roots are indeed a equals 1 and b equals 0.2, which is where the parabola is intersecting the x-axis. This method works for all of our recurrences. Let's try it on P1 and P3. If they have a solution x to the n, it'll have to satisfy these equations. Choosing n equals 2, we get two different quadratics. P1 gives the quadratic on top, and P3 gives the quadratic on the bottom. Now let's take a closer look at these parabolas. The bigger roots correspond to a of 0.9, 1, and 1.1, and the smaller roots correspond to b of 0.3, 0.2, 0.1. So the behavior of every recurrence is explained by the roots of a parabola. And here, if we put C1 and C2 on sliders, we can look at the parabolas for any recurrence we want. For example, with 1, 1, we have the famous Fibonacci recurrence. And that actually gives the golden ratio, explaining why the growth rate of the Fibonacci numbers is the golden ratio. And for our mystery recurrence, we were looking at C1 is 2, and then the second constant C2 was negative, and we were just past the point of -1. But wait, as soon as we cross -1, that's the exact point where the two roots meet, and then they both disappear. So what is happening in our mystery recurrence? Let's focus on the case where C2 is -1.01. Well, there our parabola never touches the x-axis with a minimum value of 0.01. And when we try to solve for a and b with the quadratic formula, well, right now it's undefined, since that term in the square root, c1 squared plus 4c2, is actually negative. So how do we make sense of the quadratic formula if c1 is 2 and the term inside the square root is negative 0.04? Well, the issue is that we're taking the square root of a negative number, but all the other parts are perfectly fine. And if we introduce I as the square root of -1, we see that the two roots are actually complex numbers. Well, it turns out we can use one more key Desmos feature. We can actually set it to complex mode. Now Desmos can solve the quadratic, and it finds 1 plus 0.1i and 1 minus 0.1i as the two roots. It's plotting them in the complex plane, with 1 as the x-coordinate and the imaginary part 0.1i or negative 0.1i, giving a y coordinate of plus or minus 0.1. In this geometric interpretation, a real number just corresponds to a point on the x-axis, like we had before. And we now see a really cool thing about how the roots actually behave. As we drag through -1, the parabola lifts up, and the two roots collide and then become imaginary. And what about the other cases of the mystery recurrence? Well, adding 2 more zeros brings it down to 1 plus 0.01i. Now we're starting to see a clue why I wanted 2 zeros at a time. Adding a 4th zero doesn't look very nice, but then in our final case with a 5th zero, we have 1 plus 0.001i. We'll see that our theory is still true when we plug in imaginary values. And the mystery recurrence examples were chosen to have these values for A and these matching values for B. Note that B always just has negative the imaginary part of A, which is called the complex conjugate. Geometrically, that means we just reflected it over the x-axis. The fact that one of the roots is the conjugate of each other is going to be a key point for our later understanding. To understand our periodic recurrences, we'll need to understand complex powers. I had to take 1.01 and raise it to some power n. Try to square this number and see what happens. Giving us an answer of 0.99 plus 0.2i. And now to cube the answer, we'll just take the square we had and multiply it by another 1.01i. And again, we can check our work by looking at z cubed on Desmos. Let's just look at a few more of the values and see if we notice a pattern. Looks like the real part keeps going down and the imaginary part keeps going up, but I don't really see a super clear pattern to these numbers. But pulling the board out of the way, we can see they have a pretty nice structure on the complex plane. Now if we animate the powers, it looks like it's tracing a circle, except it actually returns to a bigger spot than where it started. Letting it play more, we can see that it's actually tracing out a spiral. Now remember, 1 plus 0.1i was just the first case we looked at. For the next cases, the number got smaller and smaller closer to 1. And if we drag this parameter down, we can see that as we shift down to 0.01i, now with alpha being 0.01, it actually is going a lot slower. But if we keep letting it play, we see that the powers of 1 plus 0.01i still do form a spiral, just one that grows really slowly. It takes almost 600 steps to do the full circle. We can shrink back to the final case, 1 plus 0.001i. It'll take about 6,000 steps to do a full circle. This should be really reminding us of what we saw in our mystery recurrence. In our final case, corresponding to 1.001i, we only went through the sine wave one full time and then stopped before the second one. Then in the middle case, we were able to watch the sine wave oscillate a lot more times. It's hard to notice right here that the amplitude is actually increasing, but if we zoom out, we can see that it's actually very, very slowly increasing in amplitude. Finally, let's watch the first case of our recurrence again and compare it to what we saw from the complex exponential. Our sine wave finishes a full cycle at steps 63, 126, and 189, while our exponents also do a full loop at steps 63, 126, and 189. So the amount of spiraling out seems to correspond to how much the sine wave is growing, and the period that it takes to do a full spiral seems to correspond to the period of the sine wave. Zooming back on how we first crossed the x-axis between steps 31 and 32, that exactly corresponds to our complex number making it back down to the x-axis for the first time between steps 31 and 32. Moving back up to the next case, it crossed the x-axis between step 314 and 315, which again matches when our complex number first crossed the x-axis. And finally, our best estimate of pi came from looking at the last case between step 3141 and 3142, which again matches the case for that complex power. So where did these numbers come from? Well, notice this complex number is sweeping out an equal angle at every step. Let's measure the angle of our original point z above the x-axis. We can measure that z is 5.71 degrees up, and the sixth power is 34.26, and we do indeed see that every time we take another power, we are increasing by another 5.71 degrees. As z gets closer to 1, its angle gets even smaller, now down to 0.57 degrees. Shrinking all the way down, we can see the minuscule final angle we had. And how many copies of that tiny angle make 180? Well, there we have it. We see that number 3,141, including rounding the next decimal points pretty close to even more digits of pi. So this is showing the number we saw, but I still don't really see where that 7 degrees comes from. Things are more clear if we switch our angles back to radians. Now we see that 0.001i is at 0.001 radians. Well, not quite, because if we actually look at 10 times that, we see it's not quite perfect, but really close. We see the angle in radians is really close to whatever the imaginary component is, although it's getting a bit less accurate as we get back to our original case. So why are these numbers so close? Well, 0.1i is exactly the height we have right here. Now, the angle of this in radians, by definition, is the arc length of a section of the unit circle. Now, the unit circle is what we'll get if we line this arc length all the way up here to 1, so now it has radius 1. And we see that these are almost measuring the same distance. Moreover, as the angle gets shrinked smaller and smaller, the difference between those two distances gets lesser and lesser, until in the limit, they will exactly agree. So now the angle in z in radians is a nice power of 10, and we get back to the x-axis after 180 degrees, which is exactly pi radians. This explains why the number of steps was about pi times 10, then pi times 100, and finally pi times 1000. We've explained where the pi came from, but there's still a few more mysteries. Like, why were our sine waves actually growing exponentially? And why did the rate of exponential growth get less and less as our number got closer and closer to 1? To get a better handle on these issues, we'll need to use full polar coordinates and not just track this angle, but also track the length of the green line and the length of the orange line. Here, the length of the green line is 1.0049, and the length of the orange line is 1.05. Can you figure out what's happening with the lengths and why that explains the pattern of exponential growth? Now we have another chance to pause and play. Click the link for scene 5 down in the video description. There you can take a closer look at some of these values. Can you figure out the relationship between the magnitude of a complex number z and the magnitude of its powers, z to the n? We are going to use the magic of Geogebra to explore all of our examples at the same time and draw a lot of connections between all the theory we just saw. Welcome to parameter space. By default, we're seeing the Fibonacci numbers here. Their graph is over there to the right, as well as the whole sequence. Going to the top right corner, we can change the initial conditions. For example, making the first entry 2, we now have the Lucas sequence. This exponential growth is a bit too hard to see on a linear scale, so if we click this button here, we'll see a log scale in the z direction. There we can see the straight line tracking the exponential growth. Moreover, we can see that changing the initial conditions does not change the slope of the line. But the much more interesting part is over here on the left, where C1 and C2 can be any constants. But now, rather than sliders, we have C1, C2 as a point in two-dimensional space, viewing all possible equations smoothly morphing into each other. Dragging the positive constant C1, C2 closer to the origin, we can see that this slows down the growth rate as expected. This is especially clear if we see the slope of the blue log line decreasing, 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 until all of a sudden we now have exponential decay. And where exactly is that boundary between growth and decay? Seems like it's some sort of a line here. Clicking this Show Decay Boundary button, we see that the boundary is indeed a line. This is the line where C1 plus C2 equals 1. Along the line, we have a net 1 amount from the two terms before, and if the net amount is bigger than 1, that's exponential growth, and if the net amount is less than 1, that's exponential decay. Let's follow this line over here into the region where now C2 is negative. Recall, C2 being negative is what we had when we had the original birth and death equations. In fact, in this green region here, where we're between 1 and 2 and 0 and negative 1, we can convert C1 and C2 into a birth-death rate percentage. And sure enough, we see that boundary line corresponds to where the birth rate's bigger than the death rate, and then dying out when the birth rate is less than the death rate. But what's the real reason the sequence stays constant along this line? Well, if you recall, our theory said that this line was where one of the bases of the exponential was just 1, and we found that from a quadratic. Well, if I get out of the way, we can see that quadratic equation is automatically plotted in the middle. And zooming in more closely on the parabola, we can see that for all parameter values along this line, that constant a really is 1. Going back to our birth-death region and looking over there on the log scale, we can see that when the death rate gets too big, we get some weird behavior where the population becomes negative. Zooming into the corner of the box is the most interesting region of parameter space. Here we have birth rate winning, so exponential growth, but then when death rate wins in the corner of the box, now we're starting to see those beautiful sine waves. What's explaining the difference between exponential growth and sine waves? Well, let's look back at the parabola. We see in the exponential growth region we have two real valued roots, and right when we cross into the sine wave region, those two real valued roots collide and then shoot into the imaginary directions. Moreover, the spot where they collide looks to be exactly 1, and if we drag here to the exact corner of the box, that corresponds to where the parabola just touches the x-axis, the boundary between having real roots and complex roots. Now let's throw away the birth-death story, zoom out a bit, and ask about where the boundary is for imaginary behavior to start. Well, what we're wondering is, where does this parabola exactly touch the x-axis? We can click Show Complex Boundary and see that that boundary in parameter space is itself a parabola. If we lie exactly on the line of this parabola, that's where our quadratic equation is going to perfectly touch the x-axis. And on this side, there's imaginary solutions, and on this side, there's real solutions. Let's zoom in more closely to see exactly what's happening when we cross the parabola. Again, we go from there being two real roots to the quadratic lifting off, and now both of the roots are imaginary. So all the weird complex behavior comes from being in this imaginary region of parameter space. And where it overlaps with the red triangle, we have the purple region, where it's periodic but decaying, and in the solid blue region here, it's periodic but growing exponentially. And this boundary line seems to be the boundary where it's neither growing nor decaying. Now go pause and play with the Geogebra link for scene 6 in the video description. It looks best for me when I go into full screen with this button down here in the corner. Let's look closer at this line where the solutions are all periodic. A particularly interesting condition happens when C1 and C2 are 1 and -1. Looking over here, we see that the solution is periodic, and it actually exactly repeats every 6 steps. 1, 2, 3, 4, 5, 6, and then back to where we started. Can we see from the complex numbers where the number 6 comes in? The key here is to think about polar coordinates. Checking the complex angle, we can see that it's exactly 60 degrees. And because the angle was repeating every single step of complex exponentiation, we're adding that angle to itself 6 times, doing a full circle. 60 degrees explains why the period is 6, but why are we neither growing nor decaying exponentially? For that, we need to take a look at the unit circle in the complex plane. These are all of the points whose magnitude is 1. And if the magnitude is 1, then we will neither be growing exponentially nor decaying exponentially, because the magnitude is what keeps multiplying by itself. That also gives the explanation for what's happening around this boundary. Along this line in parameter space is where our roots are walking along the unit circle in the complex plane. And why are we getting nicer and nicer sine waves as we creep further and further to the right in parameter space? Well, moving this way is shrinking that complex angle. Let's take an even closer look at going along that blue-purple boundary. As we approach the interesting point, it looks like our sine waves are growing and growing. We're zooming into our sine waves up until they blow up to be a straight line. The behavior will be even more clear if we change the initial conditions. Let's start from 50-50. Matching initial conditions now starts us here at the peak of the cosine wave. And dragging back along the line in parameter space, we can see we're speeding up the frequency of the cosine wave, which is corresponding to the angle of A and B getting larger. Finally, let's go back to my favorite initial conditions, the one that gave the roots of 1 plus 0.1i and 1 minus 0.1i. Again, we have a sinusoid, but now starting with the initial conditions of 50-50, it looks like it's a cosine wave, where in our opening mystery we started from 0, 1, which caused it to make a perfect sine wave. The thing that I did for the opening mystery was to move up like this in parameter space, shrinking C2 closer and closer to -1 from below. Now we're getting closer and closer to 1, stopping here at the point -1.001i, which was our middle case where the roots were 1 plus 0.01i and 1 minus 0.01i. That was the middle case where we first crossed the x-axis between step 314 and 315. Unfortunately, this 3D plot seems to be pushing Geogebra to its limit. It's getting pretty laggy, so I don't think it's actually going to handle the 3000 case that we saw first. Here we are back in my favorite case, where again we can summarize the main idea. What's happening here at 2, negative 1.01? Well, again, the roots were 1 plus 0.1i and 1 minus 0.1i, which are points that are just beyond the unit circle at an angle really close to 0.1 radians. Because the magnitude is a little bit bigger than 1, it's exponentially growing, which is what we see here from the wave. And because the angle is really close to 0.1 radians, it'll take about 10 times pi steps to make it the pi radians back to the start. But there's one part of this story I'm still not satisfied with. Why is it specifically a sine wave? How is it knowing to track the height of the imaginary number as it goes up and then back down? Why not something like cosine? To resolve that question, we need to think about these constants a and b. Here I just changed the initial conditions to 30-30, which changed from a sine wave to a cosine wave. So somehow these constants are controlling what sort of sinusoid wave we have, even though its period and its growth rate are fixed by the complex numbers a and b. Let's jump back to our Desmos version of the mystery sequence so we can play with these initial conditions. Starting from 0, 1, we get this sine wave, again stopping between steps 31 and 32. But we drag them to start parallel, and now, well, it's kind of hard to see, but if we just scale everything up, which again we can do because it's linear, we see that starting from an even initial condition is making a cosine wave. That's the top. So how are those constants a and b able to decide which sort of sine wave to have? How do we know where we start? How do we know what the amplitude should be? To finish our story and explain how we can use complex numbers to fit any of these purple sine wave curves, we're going to need to move up to 3 dimensions. Thinking about complex geometry in a way that will build a widget that will be able to draw any of these sequences we want. It's time to look at some crazy complex spirals. To warm up in thinking about these constants, let's go back to the original and simplest case, just pure 21% birth, where we clearly know that the answer is 1.21 to the n. Directly changing the initial condition starts us out from a smaller or a bigger population. Changing the constant a scales our guess down or up. What should a be to fit the population? Well, it should just be p0. Now let's forget about any death rate and just turn that n-1 into n-2. What happened? Well, our recurrence actually only depends on the term 2 steps back, so it's really only a recurrence on the even numbers. If I add an initial condition at 1, we now have a separate population growing on the odd numbers. We can see clearly here that the 2 initial conditions only change the even and the odd values of p. The 2 sequences are different, but they have the same exponential growth rate as seen here on the log scale. And it's slower than that original growth rate of 1.21. And what should that growth rate be? Well, the parabola we now have is x squared equals 1.21, which has 2 roots, 1.1 and negative 1.1. So 1.1 to the n is the growth rate. But what should that condition a be? How could we simultaneously fit both of these odd and even parts at the same time? Well, that's where the second term b times b to the n needs to come in. If we have another slider here for b is negative 1.01, we can add a red term. So the blue g of n sequence is the sum of the green a of n sequence and the red b of n sequence. But man, that's hard to see with everything on top of each other. So we're going to move to 3 dimensions. Now here we are in 3D. We still have our purple population p of n and our blue general solution g of n. And we've kept them in the xy plane. And now I've scooted the green a of n sequence up and the red b of n sequence down so we can see their behavior more clearly. Now let's watch these 2 sequences grow. We can use these lines to visualize the sum of the green distance and the red distance by either adding the green distance after the red distance or the red distance after the green distance. Their sum is at the blue point here, which marks the position of g. Dragging time backwards, we can see the little contraption we built that'll draw out g for us. Let's set our g machine in motion. Now the magnitude of negative 1.1 to the n is exactly 1.1 to the n. Thus the 2 sequences keep pace in magnitude. What's happening here is the red sequence alternates between providing constructive interference and destructive interference. That pattern back and forth is what's creating the two different bands in the blue G sequence. So can we get some better intuition for our constants? Well, if the B constant is 0, we just have the exact exponential growth of a to the n. So the B terms are the ones that split our odd and even sequences apart, while the A term controls their average. So what does it look like to fit a purple P of n sequence? We use A to bring our guess close to the average, then we use B to split off the terms until they match. Now let's go back from this example to the case we actually cared about for the mystery recurrence. What does it look like to go from the powers of A equals 1.01 to A equals 1.01i? It looks like now the sequence is becoming negative. Well, to see what's really happening, we now actually have the YZ plane as the complex plane. So here's our familiar view of a power of a complex number. We see the familiar spiral in the complex YZ plane. But now that we can also view time on the x-axis, we can get a full three-dimensional view of that complex power spiral. So if this is what the powers of a to the n look like, what will the powers of b to the n look like? Well, b flips the imaginary part to be negative, which is called the complex conjugate. Geometrically, that looks like flipping across the real axis in the complex plane. So our new red spiral goes clockwise, instead of counterclockwise like the green spiral. At the moment, we're in the simplest case, where our constants capital A and capital B are just 1. So to get our guess g, we need to add these two spirals together. How should we do that? Well, bringing back the same lines, adding two complex numbers has the exact same geometric interpretation. We have the same picture as before. Because complex numbers add like vectors, we could either add the green vector to the red or the red vector to the green. Either way, their sum will be the blue point g in the complex plane. Now that we've built our g device, let's pull time backwards and then watch what curve it draws. And we can see it's drawing an exponentially growing cosine wave. This is because when you add a complex number to its conjugate, the imaginary parts cancel and you get twice the real part. So we have twice the real part of our spiral, and the real horizontal component is cosine. So did this fit the purple curve? Well, no, not for these initial conditions. But let's think about what our initial conditions are. If a and b are both 1, then the 0th power gives us a plus b, which is 2, and the first power gives us 1 plus 0.1i plus 1 minus 0.1i, which is also 2. So we just need to change our purple initial conditions to match. If we start the first value also at 1, we'll see we have a cosine wave, but it's just half as big. And then if we move up back to 2, 2, sure enough, we see that our purple curve perfectly hits. So we now have an exact solution for the case where we start at 2, 2. It's just the sum of 1 plus 0.1i and 1 minus 0.1i. So now to fully understand how to fit the other initial conditions, we'll need to really think about how to visualize the effect of capital A and capital B. Unlike before, they're actually complex number constants. So what can multiplying by a complex number do? Well, magnitudes multiply, so changing the magnitude of A will stretch out the spiral, smaller or bigger. And angles add, so changing the angle of A will rotate our spiral forward or backward. We also have the same controls for B. We can stretch out the B spiral, or we can rotate it. Bringing back our adding widget, and pulling time backward, what sort of curve do you think this is going to trace? Well, go see for yourself. You can play with this notebook now. Now it's the last chance to pause and play, with the Scene 7 link in the description. Get a closer look at these spirals for yourself. You can pan around in 3D, and you'll also probably want to use the zoom window up here to control where you see. What does the sum of these two spirals look like? Taking a look around, we can see it's making some sort of tilted ellipsoid shape in the complex direction. If we look at it just from the side, we can see it looks like a sine wave. The 4 sliders we had for A and B gave us 4 degrees of freedom. But for most settings of these sliders, we still have imaginary numbers in our blue output, and that doesn't make any physical sense. So is there some way we can restrict our degrees of freedom to enforce that we always have real valued solutions? How can we make sure to guarantee that the A times A to the n term and the B times B to the n term we'll always have all of the imaginary parts cancel so that our sum gadget here only stays in the flat, real-valued xy plane. Let's try playing with the sliders more carefully. You might guess that we want to set a and b to the exact same number. And setting them to have the same radius looks promising. We now have a nice flat sine wave. Now what happens if we set the two angles to be the same? Well, we actually have a sine wave now that's purely imaginary, so we're somehow exactly wrong. What did I do here to my two spirals when I multiplied them by the same constant? Well, I scaled and rotated them by the same amount in the complex plane. And that's actually turned my addition widget, rather than running straight back and forth like it did when these were both 1, now it's running straight up and down, and we're just getting an imaginary number. If we now just rotate the b constant, it'll actually rotate our whole sum in the complex plane. So what do we need to rotate it to get it back to be flat? Well, it seems like we need an angle of pi over 2, which is exactly the opposite angle of a. And that's true in general. If I move this angle this way, I need to move this angle the opposite way to compensate. What's true about complex numbers that have the same magnitude but opposite angles, like the constants a and b? Well, that's the definition of being the complex conjugate. If we flip this switch, we actually force b to instead be the conjugate of a. So now changing the b sliders doesn't do anything. With capital B forced to be the conjugate of capital A, and little b the conjugate of little a, this whole term is the conjugate of this whole term. What that means is no matter what we set a to, the thing we have is the sum of a complex number and its conjugate. And that just gives us twice the real part. So we figured out the correct way to go from our 4 sliders down to the 2 degrees of freedom we really wanted. So what degrees of freedom are we now controlling with our 2 sliders? Well, changing the magnitude of a, and thus also b, will change the amplitude of our wave. Rotating a will rotate one of the spirals while rotating the other spiral in the exact opposite direction. And that rotation plus its conjugate will have the effect of actually doing a phase shift of our sine wave. So our 2 degrees of freedom let us exactly control the phase shift and the amplitude of the sine wave, which is exactly enough to fit this purple curve. Moreover, it's enough to fit any purple curve, because what are we not changing here? We're not changing the period, and we're not changing the exponential growth rate. Those are properties of these complex numbers themselves and what their powers do. But because we can freely change the sine wave in its other 2 degrees of freedom, we can fit any of the initial conditions that we got from any of our mystery sequences. So that is the full answer to our mystery. And better yet, this story works for any parameters we could set. Let's go back from the smallest case to a bigger case, the middle one where we saw 314. There we have a purple sine wave with a much slower exponential growth rate. And this notebook is doing the quadratic formula for us, so we already have the right complex constants a and b. Here's the green spiral for the powers of 1 plus 0.01i. Well, technically we've still scaled it by that exact factor of 5 that was the right guess for the previous case. But we clearly have to make it bigger. Any guesses for how much bigger? Well, it turns out with everything scaling by a factor of 10, we just need to scale this up too by a factor of 10. With the scale now up to 50, we can see much more clearly that we have a slow exponential growth rate in magnitude. Let's get our adding widget back and then rewind time so that we can try to fit the phase better. Just like before, we rotate our spirals until the phases perfectly match. And there we go, we've locked onto some new initial conditions. This original mystery problem seemed to have nothing to do with complex numbers. It was literally just telling us about adding real numbers with certain constants in front of that. Yet somehow, the sine wave that these equations knew to produce was intimately linked to the complex numbers. And it was only through taking our theory, expanding the quadratic formula to get complex valued solutions, and then truly understanding the behavior of complex exponentials were we able to fully explain the sine wave behavior that we saw.